everyone. My name is Laura Caulfield, and I'm a developer in the hardware division of Microsoft Azure. My responsibilities there are in the design and pathfinding work area for solid-state storage in our data centers. Today I want to tell you about some of the technology trends and application requirements I see in this role, and the interface changes that we're adopting to support cloud-scale workloads for the foreseeable future. So first, we're going to start out with a brief primer on current SSD architecture and the priorities of today's cloud applications. Next, we'll dive into the prototype that we've been building for use across Azure. And then last, we'll explore the current state-of-the-art interface between host and drive that we're looking to develop. So first, we'll dive into the design principles for cloud hardware. Now, these tend to apply to more than just storage, but I've tailored them a bit for Flash. So first, we need to be able to support a broad variety of applications. Azure alone has over 600 different services, and we use the same set of hardware for our mail servers and our Office suite and our search engine and others. This huge number of applications is also a huge amount of hardware, so we need to make sure that our supply chain is very healthy. And we do this in part by making sure all of our devices from different manufacturers behave almost in the same way, at least in the areas that we require. We also are seeing rapid evolution of NAND generations. It's actually still following Moore's law. But on the flip side, we're seeing huge qualification times, right? The complexity of the firmware and its interactions with the host are turning the test time for any single workload into hours, and we have hundreds of workloads that could each present their own corner case that matters and is important to find and debug before we put this hardware into the data center. Last, we need to make sure that our software has enough flexibility to evolve faster than our hardware. We use SSDs for at least 3 or 5 years, typically more because they last so long. And the process for updating this hardware and the firmware is much heavier than daily pushes of software updates. So now that we've seen the environment that we're working with in the cloud, let's take a look at what the technology provides. So how many of you guys are really familiar with what goes on inside of an SSD? Garbage collection, write amplification. All right, so we're about half and half. I'll try to go quickly on the background. In your SSD, essentially, it's mostly flash memory. And each flash memory die is composed of a set of flash blocks, and then within the block, you program individual flash pages. Program, write, those two words are used interchangeably. And the flash itself has this bulk erase operation, and then you have to write to each of the pages in order. So to translate this type of interface into the standard update in place interface, the SSD has a large amount of DRAM. For every terabyte of storage, it has about 1 gigabyte of DRAM. So now when the host is writing data, for example, we have 4 streams of data. Each individual stream is sequential, but they're happening at the same time. The drive accepts this data into its data cache until it has enough data to fill a whole flash page. At this point, it updates the address map and writes the data to the flash. The host continues to send data, and the flash continues to fill up until all the flash is full. Now at this point, the SSD controller's job is to free up some flash space. It's got a whole bunch of over-provisioned extra flash space. So by this point, data has been overwritten, or maybe some applications have trimmed their data altogether, and you have this fragmentation in your data in physical space. So at this point, the SSD controller does garbage collection. It copies out the valid data, which is the main step in garbage collection, to a new block, and then it erases the old block. Now this write amplification is enemy number 1. All it does is put additional overhead in the drive. It eats away at performance. You get down to 20% of the performance in steady state for random workload. It also eats away at endurance, which is very limited in Flash and becoming more limited as the density scales up. So we looked at this and said, how are we going to reduce the write amplification? We'd like to buy these off-the-shelf parts, so let's try caching up our data on the host side, right? If we cache up a whole block and just write a whole flash block at once, we'll get write amplification down to 1, right? Unfortunately, we ran the experiment and saw a much different picture. Writing 4 megabyte random chunks of data wasn't much different than writing 4 kilobyte random chunks of data. And we had to increase the block size up to 1 gigabyte before we saw the write amplification improvements that we wanted. Now this might be okay if we have 4 streams of data, but now scale up to the hundreds or thousands of streams of data that we have, and the host side buffer cache becomes untenable. Now this gets at the heart of a fundamental design trade-off that cloud system designers see very differently from SSD designers. I've given you a hint about the cloud SSD designers, but let me first dive into the perspective of the SSD design. When you have your SSD, you've got actually a large array of flash memory, not just a single die, so you'd like to scale out your performance as much as possible. And the controller sensibly does this by caching up enough data to stripe it across a whole flash page across all the dies. So the data keeps coming in, keeps getting written, and your effective flash page size and flash block size is now multiplied by the number of dies in your device. A little M.2, for reference, has 64 dies. So this is how we quickly get up from the 4 megabyte flash block size to the effective 1 gigabyte flash block size. And this is our current state of the art, but if you look at how flash is scaled over time, as the density of flash goes up, the block size also goes up. So this is what the SSD looks like. Now let's switch back to the applications and see in particular how their design trade-offs would establish how you'd map their data to the physical flash array. We'll take a look at 3 applications, the first of which is our Azure storage backend. Now this is a lower tier in a storage hierarchy, so by this point the data is organized into hundreds of distinct streams, each went into sequentially. It's got a couple of priorities in the performance space. It can scale up its performance by scaling up the number of streams on a device. Any single stream doesn't have to get great throughput, as long as the whole system gets good throughput. And they try to keep the reclaim unit size as small as possible because this helps the end latency of their whole system. Now these application priorities map to what I call a vertical stripe. And this is where each stream is scheduled to its own block on its own die. It has the append-only semantics, so your write amplification becomes very low. Each stream is isolated, so if you trim one stream, the other one isn't fragmented. You get high throughput by increasing the number of streams on your drive, and you get the smallest effective block size possible, that 4 megabytes today, which might become more megabytes tomorrow. Our next application is a legacy application scheduled in a virtual machine. Now these tend to be, all over the map, right? But they can have small updates, they can have bursty performance. But the bottom line here is they expect the same type of behavior that they saw with legacy SSDs. So for this, it makes sense to stripe across blocks on different dies. You get the bursty performance, the high throughput for any given user. But the big difference here between legacy SSDs is that you've scheduled your VMs to different sets of blocks. So when a VM is well behaved and decides to write sequentially, it can get low write amplification without the other VMs fragmenting it. And also when you close a VM, then it doesn't fragment other VMs when it trims its data. Our last application is a new application that's still run within a VM guest. Now this, the host is still scheduling a horizontal stripe, scheduling each VM to the horizontal stripe. So the design knobs that this application has are dividing up those blocks within that stripe, perhaps for a set of different logs that it has. And so this is what I call the hybrid stripe, where you have a horizontal stripe, but then you've further striped it into vertical stripes. Now there's a few things to know. One more thing before I say that. So there's a wide variety of applications here, and you might imagine that they're on different machines doing completely different things in their own world. But in fact, to make the best use of our hardware and scale up and down with demand, we need the flexibility to be able to put all of these applications in the same SSD at the same time. So we might want a vertical stripe here, a horizontal stripe over there. We essentially need the flexibility to partition these dies out, and these dies and these blocks out into whatever configuration dynamically. Now there's a few things to notice here. All we really need is a chance to expose all these log write points, right? We don't need access to the NAND idiosyncrasies. In fact, we don't want access to those things. We want that to still be managed in the drive. And the bottom the most fundamental difference here is that as we scale up the capacity in the data center, we're not scaling up the size of each application, we're scaling up the number of each application. So to support these priorities, we've boiled it down into 3 aspects that this new interface needs to have. First, we need to replace the block abstraction with something that looks more like append-only write points, and lots of them. Right? We need the interface to have the flexibility to scale up to hundreds or thousands of write points per terabyte. We'd also like, if we're guaranteeing that we're going to be writing in this way, we don't want the drive to have to reserve large amounts of flash or large amounts of DRAM in the case that we're going to revert back to the legacy system. The next aspect that we need in this new interface is the ability for the host to place the data physically, right? It needs to be able to understand whether it's co-scheduling on the same die as another application or isolated on its own, or whether it's divided among different blocks. And it needs to be able to make the trade-off between reclaim unit size and throughput. Sorry, I've got a smoke thing going on from the wildfires up in Seattle. Okay, so the last aspect we need that has historically been kind of minimized in open channel interfaces is to keep the reliability management down in the drive, right? We're going to have some challenges, and the interesting challenges in defining this interface to make sure that the flash can continue to scale on Moore's Law. We need to enable innovation in that space for new ECC algorithms or whatever gnarliness that I'm not as familiar with these days. So taking a step back and look at these priorities, I can see how it's kind of evolved over time in the community. Right, so we've got our log abstraction, our in-host data placement policy, and our in-drive reliability. And I'm going to show some different interface proposals that have evolved kind of mostly over time. In the early days, then, the community realized that there's huge overheads in SSD storage systems, right? We designed SSDs to match what hard drives did so that we could get them into the market, and it worked. It was successful. It was a great strategy. But then people started to realize how much overhead it takes to mimic the hard drive. And so we addressed these overheads first by pulling more control into the drive. Unfortunately, this has the side effect of locking the software innovation into that pace of hardware innovation, right? You can only move as fast as your firmware is going to evolve. And you can't try new things between the software and firmware in a very agile way. So next on the scene were multi-stream SSDs and IO determinism. And this is where we started discovering the benefits of isolating different users down to the hardware. And also some of the benefits of, some of the ways to place the data in the drive. Unfortunately, the constraints in this space are kind of a double-edged sword, right? Both of these interfaces support legacy I/O patterns, and so they retain all of the DRAM and flash overheads that are required to quickly revert back to those legacy I/O patterns. And so then the final set that we're considering here are in the open channel space, and this can mean a lot of things. There's a huge spectrum of proposals there, and there's a lot of evolution that's happened recently. And so my point here is that we need to make sure that this interface evolves so that the media management can stay in the drive and that these systems can become production ready. So our next steps are to take this interface and further develop it into a production ready system. So now that we've evaluated applications priorities, technology trends, and some of the available options for the new interface, then our next steps here were to build a proof of concept and evaluate the overheads and performance that it gets. This is also our first step towards creating a system that's viable for a replacement for a conventional storage stack, right? We still have to support those legacy applications with the same level of performance as conventional SSDs. So let's start out with defining a few terms, since so many people have so many different definitions for the same set of words. Open channel SSDs, this at the kernel of it, we're exposing physical access or physical addresses from the drive to the host, such as channels, right? So the channels are open. We're also going to be talking about the flash translation layer. This has conventionally been in the SSD's firmware, and we're starting to see separate into two distinct parts, one called log management, one called media management. Now, the log manager's main role here is to receive any kind of write, maybe an update in place, maybe a log structured write, and to emit I/O patterns that are definitely sequential, maybe to one or more write points. And in order to do that, then it maintains the address map and performs garbage collection. The media manager, their main role is to basically translate the gnarly physics of flash memory into something that looks more like a software logical sequence for how to access media. So this set of algorithms is conventionally like ECC algorithms, read, retry, read scrubbing, all the things that change with the NAND generations and across vendors. So with these terms in place, now we can talk about open channel and the two main variants. So here on the right, we have next to a standard SSD on the two ends of the spectrum for open channel. So in standard SSDs, the entire FTL is down in the SSD, right? In the early open channel SSD systems, including our prototype, that entire FTL is shifted up into the host. This includes the media management and the log management. And this gives us the best flexibility for playing around with these algorithms and understanding the best division of labor between the log manager and the host manager. But this isn't a system that I can take to my boss and say we can take to production, because the drive can't be warrantied. I have to recompile the host side driver for every new NAND generation. So it's important that we reach this final destination where the media management is pulled back down into the drive. All right, so without further ado, here is our open channel prototype running in what we call a Windows Cloud Server, basically the type of server that runs in Azure and our other applications. On the right, we have the prototype card. It's not our standard M.2 form factor because it's a prototype, but it has essentially the same architecture. It's also running here in the disk manager, and the two black screenshots are of it running, the system running under our conventional qualification tools. In the center, we have store score running the standard four corners that you hear about: random read, random write, sequential read, sequential write. And then in the bottom left corner, we have a tool that can do secure erase and some of these other operations. And it's exposed as an open channel type of SSD. So this is a very real system. It's pretty exciting to see running. One of the first things we wanted to measure is what opportunity we have for optimization, right? We all keep talking about reducing the map size and reducing the total end-to-end CPU overhead by reducing the total amount of work. What do those overheads actually look like? So we looked at three areas. The first of these is write amplification, right? This is enemy number one. We want to reduce that as much as possible. We look at a reasonable worst-case workload, which is highly fragmented. This is a 4K random write workload. And in our normal SSDs, we usually see a write amplification factor between 4 and 5. In this particular system, then we saw a write amplification factor of 4, and it moves from not being in the drive now, but the amplification is happening in the host. Our next area that we looked at was memory. Now this is essentially the address map. So when you do a 4K addressing, then you have the 1 gigabyte of DRAM for the 1 terabyte of flash. And that's exactly what we saw, right? Our memory usage went from 1 gigabyte in the drive to 0 and in the host from 0 gigabytes to 1 gigabyte. And this one is an easy one to optimize for applications, right? If I/O patterns start shifting from 4 kilobytes to 8 kilobytes, then right away you can reduce your granularity to 8K, and you won't get that performance hit of read, modify, write, and you don't have to lock your decision into when I'm manufacturing the hardware, how much DRAM do I have to put on my device. It's dynamically available. The last area we looked at was CPU overhead, right? We're shifting all this work up into the host now. It's doing more activity in the host rather than in the drive. Now, there's some overheads in this system that are specific to the prototype, right? There were design decisions we had to make to get the prototype out the door. And in our next iteration of software development, those will go away right away. And then beyond that, there's further optimization we can do by just reducing the overall activity, right? Same time we reduce the write amplification, we'll be reducing the CPU activity as well. So the big takeaway here is that we've quantified the overheads. Now we understand how much optimization opportunity we have. We also need to make sure that we're addressing those legacy applications, right? We can't ask everyone to rewrite all their applications to get the savings. So we need to make sure they're behaving at least at parity. So I'm happy to say they are. Here we've just run the 4 corners plus a mixed workload and measured the throughput. In gray, we have the average of our standard SSD that we're calling right now. It's an average of 3 SSDs. And then our open channel SSDs in green, and our standard SSDs are in various shades of blue. So in looking at this, you can get the high-level takeaways. Basically, the read performance is fantastic. It's in the top of the class or even better. The write performance is a little on the low side, but these FTL algorithms also haven't gone through the optimizations that FTLs typically go through right before shipping. So I have every faith that that write performance will come up. The second workload that we looked at is notoriously challenging for SSDs, but it's one that I smile because the application designers every month or two come to me and say, what the heck is going on with my read performance? And basically it's a mismatch in what's going on in the background activity. So they're doing writes in the background. Oftentimes the benchmarks aren't doing writes in the background. So in this one we are doing writes in the background. And this SSD does just as well, if not better, than the other SSDs. I'm showing average latency in the purple, and then scaling up through 2, 3, 4, 5 nines percentile latency, and then a maximum latency run over about an hour after preconditioning. So the open channel SSD here gets maximum latency better than 10 milliseconds, which is better than the other drives. And then the other 2 through 5 nines latency are about on par. So overall, this proof of concept has been very successful, and we've seen that legacy applications can perform at parity, and now we've set up our system, and it's ripe for optimization by all of our different application groups. So then our next step is to make this system production ready. And the important part here is to make sure that all of our SSD vendors can implement it, and we have a standard interface that works for all of them. And so in the next section, I'm going to dive into what we currently have in the current state of the art for the interface that we're looking at. At the core is the physical page addressing interface, right? We keep talking about having a physical address. So the address format now, instead of having logical addresses, has a segment for each of the main architectural elements in an SSD. You have your channel, which is SSD channel. You have your parallel unit, which maps to a NAND die. You have a chunk, which maps to a multi-plane block, and then your sectors and pages. Now, all these addresses map to a physical location, and they don't change, which also means that the host is exposed to the access pattern required by the flash, right? We have to erase a whole chunk before writing any of the sectors, and then we have to write the sectors sequentially. This last bullet here about the cache minimum write size is pretty cool. So this is one example of how we're defining an interface that works for how NAND has scaled in the past and exposes a logical thing that the host side software can work with. Let me tell you more about what I mean here. Basically, your NAND cells, your memory element, contains more than 1 bit of data, right? Your MLC typically has 2 bits, and then your TLC has 3 bits. And anytime, so these bits are also split across different pages. So it's possible to write one page and have your memory element half written. And when it's half written like this, then the written data is more susceptible to errors caused by reading of this data. So one of the gnarly things that SSDs do now is make sure that you're not reading from those half-written memory elements. Now, enter cache minimum write size. Basically, the contract between the host and the drive is now to say, don't read from these last n pages of data. Make sure you cache at least n kilobytes of data and read from that cache instead of reading from the flash physically. Now you can take this another way and say, well, let's take that cache and put it in the drive. Let's hide it from the host. And in that case, then you just expose a cache minimum write size of 0. There's a funky little animation here I didn't go through. But basically the picture on the left here is a picture of your memory elements. Each row is a memory element, and then each column is a different bit in that memory element. The numbers are the pages in order. So at this point, we've written up until page 18. Now we write page 19 and half fill that memory element. Now we write page 20, and then at page 21, you've filled that memory element, so it exits the window of the cache minimum write size. So this is kind of a hint at one of the things we're going to have to do to define a good interface that works for the drive and for the host and scales with new generations of technology. The next one you're probably familiar with. It's a trade-off that's been going around in the I/O determinism circle as well. And basically, we have a trade-off between providing good quality of service and providing good reliability. I'm seeing some smiles back there. Basically, as soon as you break up your RAID stripe, you stripe across dies, right? And as soon as you break that up to get good quality of service, now you don't have your RAID providing you good reliability. So RAID and isolation are at odds, and this is an ongoing discussion that is being solved in the I/O determinism space and is overlapping with the open channel space. So we really do have a spectrum of interfaces here, and we're going to find some place in the middle that addresses hopefully both sides. This last bullet here. So in the cloud, we have the benefit of sometimes, in some applications, doing a higher level of replication that can provide the higher reliability. So this is what allows us to maybe reduce the reliability provided by the drive to a known lower level of reliability because this higher level of replication can rebuild the data. Okay, and then my last topic on the new interface is kind of scaling back a little bit from the pure physical addressing. So we want to do physical addressing, but in moderation. Even in SSDs, we saw how they remap bad blocks through a sparse map. So it's kind of a low overhead option. And I see a similar thing possibly happening with open channel. Basically, at your block level, then you have bad blocks show up, and you want to perhaps have a sparse map to map those out. But if you make your block logical, you can also have the drive provide wear leveling guarantees at the LUN level. So now you kick your wear leveling into these two parts where the drive guarantees a die level wear level, and then the host uses its normal migration patterns to wear level across the dies. So in terms of wear leveling, we're kind of moving our boundary from the drive level to a LUN level. And my final point, which I didn't write up here, is that we can do this with a block, but maybe not with a page or a channel, because your block in Flash is independent of physical location, right? I expect the same guarantees from block 2 as from block 3. And if I schedule two applications in the same die on these two different blocks, I can kind of map it around and not notice any difference. And in fact, that's even more the case with NAND than it is with hard drives. Okay, so I'm actually finishing a bit early with the conclusion, so I'm hoping we'll have a good discussion after. We've seen over these slides that it's important for us to architect this interface to address both the cloud scale that we're seeing today and the cloud scale we expect to see in the future with hundreds and thousands of workers per terabyte. But we also want to make sure we have the correct division of labor to allow NAND to continue to scale. I show you our proof of concept and the data that we got out of it, basically showing the system overheads and how we're ready to optimize at the application level with this open channel interface. And the final steps that we have to do to bring this production involve the whole community in defining this interface. Which brings me to my final solution, my final point. The final solution for this interface needs input from the whole community, right? We want it to work for all of our different drive designs, for all of our different hyperscalers. So it's a great time to jump in and talk about what this interface should look like and what things we need, what mistakes we need to make sure we're not repeating. So with that, thanks for your attention, and I'm happy to take questions now. Yeah.
Timeline, what's your projection? How are you taking this production timeline? What's your hope or dream?
Timeline for production. So I hesitate to say because I haven't finalized this with everyone. But some things I can say is that Open Channel, we hope to be faster to implement on the drive side, right? We don't have to have each vendor implement new FTL algorithms and vet them out. And we've already done the majority of the work of getting the complex FTL algorithms working in the host. So next step is getting the interface defined, and that's hopefully kicking off now. And once we have that, maybe a year after for final hardware. Yeah.
You mentioned that there are different kind of applications that you want to support. For example, there's a streaming application where there are multiple streams, and it's best for each stream to have a narrow stripe, just go through one time. And there are other applications such as VMs where it's bursty and it's quickly striped. So in the final solution that you're proposing, do you have some sort of dynamic approach?
For basically building that picture.
Yeah.
Yeah, that's what I would like to see, and that's the way everyone in the company is talking, right? It's how they already operate.
And somehow the amount of buffering also needs to factor in here, because ideally you would like to buffer as much as possible, so you can then leverage the bandwidth to all of the.
You're saying like buffer up. Sorry. Like for the first application, make sure you buffer up enough to fill all the dies with your write. What kind of buffering are you thinking?
The assumption, I guess, is that you have some finite amount of persistent buffer.
Ah, yes. So there's persistent and non-persistent as well. And that, I mean, it all happens case by case, right? You talk to this application, they say, yeah, it's okay if you lose that. Most of the time, the data center's powered on. Once in a blue moon, it'll be powered off, and I've got replication to pull it in from elsewhere. So in that case, it doesn't need to be persistently buffered. In another application space, maybe they're making really small writes, like 200 kilobytes, and so they're not able to fill up a whole flash page, and they don't want to rework their system to basically handle that data loss. So then they slap in the persistent memory buffer to fill up a whole flash page.
So this is going to be described somewhere in kind of algorithms they're using to construct stripes.
Good question. So the way I see it, so I don't specifically have plans on publishing that kind of thing. The way I see it is once I get the interface going for people, there's going to be this explosion in the application space where, there won't be the necessity to change your application, but people will start to see, oh, I can schedule my data in this way, and my write amplification goes from 5 to 1. So why wouldn't I enable that new technology that has 20% the endurance? So I think you'll see a lot of interesting work come out all over the place in how to do this striping. Yeah.
For the minimum cache write size, that's addressing a specific problem of the register effect on your lots terribly written. In the future, how do you keep these, let's say, NAND quirks from propagating up into the interface or up into the host? Because each NAND generation is just going to have its own quirks.
Yes. So I highlighted this in part because it's something that we've seen on many generations, right? Anytime you have a multi-level cell, as it gets denser, then it gets harder to manage. But the thing that's consistent is that you need to cache the last n pages. So my goal in this space is basically to rely on the community expertise to say, this is what Flash has been doing for the last 10 or 20 years, and this is how we expect it to continue to behave. These are the patterns that we're seeing. So
on the device side, sometimes we don't find this out until we have the memory in our hands for a little bit, and it's pretty late when we start to find out some of these things, especially at higher endurance.
okay.
So it's very hard to provide insight on what we expect the NAND to do.
Yeah, I'd love to talk with you more about, like, I don't know what you can share, but say again?
I'm sorry, I question is, why would the host need to know that? You can still, in our model, you can still manage that transparently on the device.
Well, this is an example of one that's not fully transparent.
But it could be some kind of, in the device handle it. The disk pages that you are having, you don't want to compare the DRAM on the drive. And then you can have that on the node. But if you want to carry the DRAM on the drive, you can have it extra.
I think what you're saying basically is that what we have now with current SSDs gives you a lot of wiggle room, right? You can come up with all sorts of creative solutions for managing the errors that you see pop up late, right? So I agree we need to be careful with how we change that to make sure that you still have freedom to do those things. But kind of the abstraction we have right now is just requiring so many overheads, and we're repeating algorithms across the whole stack.
I mean, because you kind of opened up talking about the long test times and fall times, and now it just may shift from, say, the device. It may just shift it. It may not improve.
Yeah, there is that danger. Yep.
So my question is more just to you as a system designer with respect to streams. So you've used streams before, did you get a chance to test that out?
We've been playing with them, yeah.
So I'm just curious because from box OEMs, guys that we've talked to that have used them, there's this finite number of streams, which I can only imagine is far worse in hyperscale. And how do you coordinate those streams, given that they're finite, they're ephemeral, with the fact they're limited, and then how does the FTL deal with the fact that it only has so many streams? How does that all work practically speaking?
Using the FTL on the drive side, or?
Just what's the success been with streams, given that there's a very finite number of streams, and you guys are probably creating tons of them, and it's very dynamic.
Yeah, so that's a great question. Basically, streams as they are now, you basically get 8 or 16 streams in a terabyte, and we're seeing adoption, but it's limited. So only one of the many applications I see, it's a big one, but only one of them has actually found the benefit worth the extra implementation they've had to do. And another application is taking that and saying, well, I still need hundreds of streams per terabyte. What if now I guarantee you that I'm only going to write sequentially in each of those streams? Can you provide me that better scale? And the answer is looking like yes. But again, it's kind of a minor step, and it applies to one more group. But then there's the next group after that I've found in the last couple months who want thousands of streams per terabyte.
What I don't hear anyone talking about, though, is how an FTL can possibly keep track of thousands of streams.
Yeah.
Hundreds.
Yeah.
And there are none that do today. And the resources for that would be amazing. And coordinating that with the host.
Yeah. You're just adding overhead in order to do these things. And so one of the major goals with Open Channel is to strip out a lot of those overheads and make the whole system more efficient, instead of having everyone tracking more and more stuff on their respective sides of the fence.
But more importantly, mean, the whole point of NVMe was to simplify things, right? So, I mean, one of the reasons for success in that was that it was easy. It was very easy to implement it, and the problem shifted down to the device. So, so the device has to deal with solving that. All of a sudden, we're bringing this back up. I mean, is there enough value? Do you believe that there's enough value to bring that management back up into the operating system or user stack to warrant, to warrant this?
Yes. Yeah.
So you're going to think you're already doing storage stack. So if I have block structure application, file system, whatever, if I eliminate all three, and just have one classical and physical system, then that helps. And then I have actually this over that we can always have the benefit I had along.
Because I'm trying to say, how does that eliminate the things you need to do in the file system?
That wouldn't be a problem. It will just bypass it.
So what do you need file system? For your application? How do you reconcile? Is that completely rethinking the entire storage stack from the application down, or is that something else again?
So everywhere.
Yeah, so I mean, one of the challenges in discussing these concepts across Microsoft is that each audience member has a different benefit that they could get from Open Channel, right? So when I talk to the qualification team, then for them it means they can put the drives into the data center sooner, mostly. And it's gnarly talking about like getting the same hardware working for everyone, right? So we've essentially shown that it can work for everyone at parity, and those who want to make it better have the chance to optimize up to 5x write amp reduction, which right away translates to now use QLC instead of TLC, which is at least N% cheaper, and get performance up 5x what it was before. And part of the reason that the benefit is so great is that we share our hardware massively, so we don't have the situation where we get the low write amplification. There's almost no applications in the data center that can own a whole SSD. So getting it striped out to a large number of people makes a big difference. Yeah.
So I'm a little confused by why you think this will actually speed up drive qualification.
Okay.
With a new generation of drive comes out with XLC that requires entirely different algorithms for some of these management and stuff. It seems like it will take a lot longer for that to percolate up into the file systems and application layers and stuff, and slow down the introduction of new technology. And before all of that gets rung out, now the drive vendors have the device providers have the ability to work out those algorithms, embed them in the device, and provide something that is functional and working at the interface level.
So
Not interdependent with the
yes.
massive amounts of operating systems and firmware.
Yeah. So I see the emphasis in a very different way, right? This interface isn't going to work if it needs to change with every NAND generation. So we haven't done our job and we haven't finished it if it changes with every generation. The thing that I do see every day is a new NAND generation comes out. It's almost no different, right? You've changed some parameters. The silicon's even the same. You just get into test mode and you do some tweaks. And yet you have to go through the full qualification process. And there's two aspects to that make it so long. Every time you do a new workload, you have to run it for 2 hours, right? You're not going to get consistent performance if you run it for 5 minutes, because you have to precondition, you have to warm up the garbage collector. And I don't see that happening with new tweaks to NAND management that have to happen. I don't think you're going to come up with something that requires 2 hours of testing each workload. And I also don't think you're going to come up with something that has corner cases in one of 500 different workloads that I could run on the device. So I see the emphasis in a much different area with very little changes to our current interface, to our current NAND generations. We have to run a huge amount of qualification.
Actually, to add to what you just said, I was saying that the log management would not change so much.
Yeah.
Media management might change, and
Exactly.
that would need to run.
Yeah.
So, for example, ECC, etc., and various optimizations at a physical level that can happen within the drive.
Yeah, and for reference, I mean, look at other devices, right? They make little changes or even big changes to the media that's in the device, and they rerun their qualification. The workloads they run, they can run for 5 minutes. With SSDs, I mean, every other week I'm telling someone new, no, you can't run it for 5 minutes. You're not going to get the same performance. And it's people don't realize the overheads it takes to qualify an SSD and how different they are from other devices. So, yeah.
So, in your prototyping phase, how many different types of NAND did you actually play with?
Just the one.
That's
Yeah.
a problem.
That is a problem, yeah. So,
I
yeah.
will find myself in the space for a while. Your expectations have changed and is small.
So I've used one. Mattias, how many of you played with
Hit a
We
little bit
have all
up.
the major
Okay.
TLC.
all the major TLC? Okay. So
I think we have.
we've done one prototype. He's done, yeah.
It's easy. I understand this, and it was.
But the FTL changes as they change the hardware.
Yeah.
Yeah.
You're missing the fact that media manager's still in the device. All the things to do with disturbs, data retention, and nastiness stays in the device. It's just putting the address translation and the garbage collection commands in the host. All the stuff you're speaking of stays in the device.
But garbage collection and other algorithms do change in the FTL as they change.
Yeah.
They can be decoupled.
Yeah, and I don't mean to minimize this decoupling, right? This is going to be our biggest challenge, right? We have to come together and figure out what this division of labor looks like to get it right. And that's,
My fear is that you come out with 6 LC, whatever,
yeah, yeah,
and yes, your stuff works, but the thing dies after 2 months. I mean, that's what I'm saying. I mean, the idea of this, of that, how much interplay between the two layers is necessary.
yeah.
We're assuming right now that it's not much.
We're actually seeing the opposite, right? So we're talking about people using open channel in order to enable QLC, right? Our applications can't use QLC because the write amplification is too high.
I definitely like the idea of getting the DRAM out of the drive.
Yeah.
I like that.
That would be fantastic. DRAM out, use half the flash again.
It's like, why is there so much DRAM?
Yeah, yeah. I mean, that's an easy win once you get the remapping in the host. A lot of the applications are already doing that mapping, so it just goes away. So, all right. I think they're going to kick me off in a couple of minutes. So unless there's other burning questions, thanks for the discussion.